Swayam Prabha. Digital India. Educated India.
See, we have been discussing concepts related to stress. So, now you know fairly well what is the concept of state of stress at a point, and you could understand the concept still better by looking at the graphical representation of Mohr circle. From the Mohr circle, what you learned? You learned there could be planes that are very special. One such set of planes are known as principal planes, in which the stress is totally normal. And we have also looked at other important planes in which the shear stress can reach a maximum. We also learned when shear reaches a maximum, in general, you will also have a normal stress. Fine. So, you have fairly good idea of what is state of stress at a point. And we have also looked at Mohr circle in 3 dimensions, and you will appreciate still better the utility of Mohr circle and its simplicity when you look at other graphical representations. Fine, these were developed well before Mohr circle, and you find that Lamy stress ellipsoid was developed in 1833. All this is possible once you understand the representation of stress tensor in the form of a principal stresses. That makes your life simple, and your stress tensor also has many zeros. So, any mathematical manipulations that I want to do can be done quickly. And what is done in this approach is, you plot the stress vector, the magnitude of the stress vector passing through all the possible infinite planes. You have the plane and you have the expressions for the x component, y component and z component. This graphical representation is credited to the scientist Lamy. So, you have the plane, on this plane you have the stress vector, and when you plot it for all the possible infinite planes, in general it takes the shape of a ellipsoid. That is what you see here, which can also be mathematically proved since we have very simple expressions. We will see that subsequently. What we are plotting? We are plotting the magnitude of the stress vector. Fine. And how you have this coordinates? The coordinates are nothing but Tnx, Tny and Tnz, and you know the expression for Tnx in terms of the principal stress and the direction cosine. And you also have an identity that nx squared plus ny squared plus nz squared equal to 1, which is a very well known when you look at the direction cosines. So, now when I decode using this expression, I get the expression as Tnx by sigma 1 whole square plus Tny divided by sigma 2 whole square plus Tn as z divided by sigma 3 whole square, that equals to 1. So, this is nothing but an ellipsoid of revolution. But you get only the stress vector. But what we found, more than the stress vector, I need to get the normal stress and shear stress. So, there was also another graphical representation. Have you been able to take down the essential of this slide? Have you? That is the reason why I spell out the equation. When I spell out the equation, you have time to write that equation. Even if you have not written it completely, you can prove it later by understanding we have just used nx squared plus ny squared plus nz squared equal to 1. That's all the simple expression that we have used. Okay. So you have the other graphical representation called Cauchy's stress quadric. Here he attempted to plot 1 by square root of sigma, that is the normal stress acting on the plane of interest. In the previous case, stress vector was plotted. In this case, you have a graphical representation for various representations of the principal stresses. If I have all of them non-zero, I will have this as an ellipsoid, and here along the normal you plot PQ, whose magnitude is 1 by square root of sigma. The other understanding is, suppose I plot whatever the surface I get, I find out the normal to this surface at the point, that would be parallel to the stress vector at the point of interest. I am not getting into the proof. So you can understand these graphical representations are too complicated. And when I have a situation where sigma 1 equal to sigma 2 and sigma 3 is different, I get this central core as a circle. You have a special form of ellipsoid, okay? Ellipse all other places, but it is a circle at the center. Suppose I have a situation sigma 1 equal to sigma 2 equal to sigma 3, you get a sphere. What way we got it in Mohr circle? If I have sigma 1 equal to sigma 2 equal to sigma 3, we just got it as a point. Fine. So it was a very simple graphical representation, very elegant. And even for other cases, even if when I come down to a planar situation, you get beautiful geometrical patterns. And this was credited to Cauchy, and we have already looked at Cauchy was responsible for establishing the concept of stress tensor. That happened in 1822. Fine. Suppose I take a plane stress state, if I have sigma 1 is greater than sigma 2 and they are both positive, then I get this an elliptic cylinder. So likewise, they were so happy. See, in those days, any graphical development was considered enjoyable and people were comfortable with it. And it also adds to the happiness of the scientist that he had beautiful patterns. Suppose I have sigma 1 equal to sigma 2. In a two-dimensional situation, it becomes a circular cylinder. And what was it in the case of Mohr circle? When sigma 1 equal to sigma 2, it was just a point. And you also have very complicated shapes when sigma 1 is greater than 0 and sigma 2 is negative. I get this as a hyperbolic cylinder. It was difficult for me to plot, so I left it. And when sigma 1 is not equal to 0, that is a uniaxial stress state, you get two parallel lines. From a graphical point of view, when people were groping in the dark, this gave some light, and there is no specific year when was this developed, but it should be much before Mohr circle. It was credited to Cauchy, so it should be before 1857. Fine. And when was Mohr circle developed and stabilized? 1882. That is 60 years later, stress tensor was understood completely. Okay. So you find with these other examples of graphical representation, Mohr circle is the simplest. It is just a circle for any state of stress, easy to draw, easy to get all the information that you need from stress analysis point of view. And you also know that Mohr circle you could draw based on the stress transformation law. And we developed stress transformation from the first principle Again, I am repeating the same thing which we have done in the earlier class, because it's a very fundamental concept. So, when I say t x prime x, I am talking about plane x prime, and I have a stress vector. This can be achieved by the Cauchy's formula, and if I want stress tensor with respect to x prime y prime axis, I will have to do a vectorial transformation of the stress vector. Fine. If I have to get t x prime from t x prime x, I have to go for a vectorial transformation. And this is so important. Until you graduate your mechanical, you will be having requirement to use this again and again. So, it is worth learning how to do it from first principles. It is also worth to do how to do it quickly. So, that is what we are going to see in this class. From first principle you can always derive, takes time, and some of you have very good memory. You may even memorize these expressions, but when you come to the examination, you will have a confusion whether this is plus 2 tau xy or minus 2 tau xy, because when I have the expression for sigma y prime, I will have a negative sign. So, now we will look at from a different perspective. You need to know and master this aspect also. So, what I am going to do is, I will directly write the stress components in the reference axis x prime y prime using indices. And what is given to you with respect to the xy reference? You are given the stress tensor at that point, and you also have knowledge how to express x prime y prime in terms of x comma y, and you are given the stress tensor. And note this, the way that I have written. What is it that I have written? I have written it in the way we originally developed. I have not used the equality of cross shears. I have said this is tau xy and this is tau yx. So, when I use indices for me to calculate sigma x prime, I will have 4 terms in the expression, and all these 4 terms should appear without using the advantage of equality of cross shears. And what is important here is, I should write the stress transformation, the vector transformation matrix properly, the rotation matrix properly. That you can easily understand. See, I have this x prime. This x prime is definitely longer than x. So, it will be x cos theta plus y sin theta, and you will have y prime is minus x sin theta plus y cos theta. That is a mnemonic way of remembering it. If you put the x prime, y prime and xy as for a generic point, you can write this. If you write this rotation matrix correctly, you can straight away write the transformed stress component directly. What I want sigma x prime. This will have contribution from all the terms. So, I take sigma xx, and what I do is, I have x prime x, and what is x prime x direction cosine here? Cos theta. So, I will have cos theta. This is again x prime x, so I have cos theta. Then I go to the shear stress component. I have x prime x cos theta. I have x prime y, that is sin theta. And I go to the next term, tau yx. I have x prime y is sin theta, then x prime x cos theta plus sigma yy. I have this as sin theta multiplied by sin theta. This is straightforward. So, I get the final expression in this form, and this is also simplified in terms of sin 2 theta or cos 2 theta, whichever the case may be. This is straightforward. Is the idea clear? We will repeat it for tau x prime y prime. So, do not invoke equality of cross shears while using this approach, that is very important. In this expression for tau x prime y prime, you will understand why I want tau xy as well as tau yx. Their multiplication factors will be different. Fine. So, when I use these indices, you will have to do this. Can you do it? Can you do it and check it with my slide? You do not have to remember. Please do it. Take a minute to do it. I should see everybody doing that. So, if you learn how to write the transformed stress magnitudes based on indical notation, the key point is you should write the rotation matrix. Even if I have forgotten the rotation matrix, if you go and put these axes and take a generic point, then you can construct this. If you construct this properly, rest of it is simple and straightforward. That is a key element. Fine. So, I have this as cos theta multiplied by minus sin theta, and when I go to tau xy, I have x prime cos theta, y prime y, that is cos theta again. Okay. When I go to tau yx, I have x prime y, that is sin theta, and then y prime x minus sin theta. You find these two terms are different. You get the point? So, if you use the equality of cross shears, using the indical notation to get the transformed stress components, you cannot apply. So, you should understand the restriction. And you similarly write for sigma y by, I get this as x prime y and then y prime y. So, I have this and this is written in a simplified fashion here. So, I have tau x prime y prime equal to minus sigma xx minus sigma y divided by 2 sin 2 theta plus tau xy cos 2 theta. This is the same expression that we got from first principles also. You should know how to write it from first principles, but you should also know how to solve problems where you have to write the expression. You should not have difficulty in assigning the correct signs. Okay. So, this is a recipe for you to do that. I can repeat the same thing for sigma y prime y prime. Can I expect you to do that? Okay. I think I would appreciate that you do that. I am going to show the result and do that as a home exercise. Okay. Because that will help you to appreciate the methodology involved, so that even when you are asked to wake up from your dream, you should be able to write the stress transformation, because this is so fundamental and important for all your future courses. Okay. So, this is a summary you have. I have the stress tensor referred with respect to x, y frame, and then I want to find out the stress tensor referred with respect to the x prime, y prime frame. So, I have the summary of results. This is nothing but the summary. You can just verify whether the expressions that you have written are correct. And the message in this is that you have to write this rotation matrix and also put this x prime y prime here and xy there. If you interchange that, then again you will have a problem. So, you should know how to write the rotation matrix and what we are looking for. Fine. Then using the indical notation, it is very comfortable for you. See, from Morse circle, you have already have an idea what are principal stresses. While we developed the Cauchy's formula to find out stress vector on any arbitrary plane, I said you can find out two classes of problems. In one class of problems, the direction cosine is given and you have to find out the stress vector. In another class of problem, specify the stress vector, find out the direction cosines. Precisely that is what we are going to look at when we want to find out the principal stresses and principal planes mathematically. You already have the result from graphical representation. Is that idea clear? Mohr circle was so useful. So you have an idea that you can have planes where you will have only normal stress. That idea is now very well understood. Okay, now we ask the question mathematically and we specify the plane to be n, and the direction cosines are nx, ny and nz, and we also specify what is the stress vector. We have specified on that plane I have only normal stress component. So that means stress vector is specified, there is no shear stress component. And I want the stress vector to be in this form, which could be identified from the Cauchy's formula. I have Tn equal to sigma n, and components of this along x, y and z axis are, we have specified this. I have specified the x component is sigma nx, y component is sigma ny and z component as sigma nz. This is what I want. What is unknown here is the direction cosines nx, ny and nz. I am not sure whether you have studied eigenvalues and eigenvectors in your mathematical courses. So if you have done that, then we are going to formulate this problem as an eigenvalue and eigenvector type of development. Okay. So from Cauchy's formula, I have the generic expression. This is the given stress tensor, and I have this direction cosines nx, ny and nz. And in this specific problem, we have specified what should be the nature of stress vector. The stress vector should be of this nature. The question is how to find out nx, ny and nz. Is the idea clear? So now I can combine these two. I can replace tnx, tny, tnz in terms of this, and I can do a mathematical simplification, and I can rewrite this in this form. I have this as sigma xx minus sigma, tau xy, tau xz, tau yx, sigma yy minus sigma, tau yz, tau zx, tau zy, sigma zz minus sigma, multiplied by nx, ny and z, that equal to 0. So what are our interests? We need to find out what are the possible values of sigma and what are the possible values of the direction cosine nx, ny and nz. In realities, you can have this as an eigenvalue and this as the eigenvector. Is the idea clear? And obviously, I want to have a non-trivial solution. If I have nx, ny, nz 0, everything goes to 0. We do not want that as a solution. For a non-trivial solution, what I should have? I should have the determinant goes to 0. See, you have to get the determinant, but I will try to make your life simple and faster. I will rewrite it in a convenient fashion. The final expression of this determinant can be written as sigma cube minus I1 sigma square plus I2 sigma minus I3 equal to 0. And we will soon understand why I1, I2 and I3 are called stress invariants. We have just given a definition that these are stress invariants. Now I will also have to define what is I1, what is I2 and what is I3. Once I define what is I1, I2 and I3, it is easier for you to write the expression for the determinant comfortably. to make your life simple and also to have your involvement in development of these expressions. I1 is given as sigma x plus sigma y plus sigma z. It's a very famous invariant, and we should also know how to use this invariant effectively in our computations. And you have the definition of I2. So, look at the I2 definition. It is very interesting. If you see the animation, you will never forget how to write I2. So, I2 has sigma x tau xy sigma yy taken as the first 2 by 2 portion of this 3 by 3 matrix plus this portion of the matrix sigma yy tau yz sigma zz and all the 4 corner elements. So, if you know how you have sequentially written down I2, you can easily write out from the given stress tensor. I want you to compute this I1, I2, I3. You can quickly compute I2, it is not difficult. Please work it out and check it with my expressions. Okay. What I have said is, when I say this determinant should go to 0, I should get sigma cube minus I1 sigma square plus I2 sigma minus I3 equal to 0. I1 is straightforward, no computation involved. I2 you have to write down the expressions. Similarly, I3 also I have to write down the expression, and I3 is the determinant of the complete matrix like this. So, I3 is the determinant of this matrix. I will read it out: sigma xx tau xy tau xz, tau yx sigma yy tau yz, tau zx tau zy sigma zz. So, the idea is, if you find out these, you can write this expression comfortably, and let us see the expression in the long hand. Okay. And finally, once you get these quantities, I will have 3 roots for this expression, and they have to be arranged algebraically. The largest is sigma 1, in between one is sigma 2, and the least is sigma 3. This you should never forget. There is a convention in how to label sigma 1, sigma 2, sigma 3. It is not that arbitrarily whatever the roots that you get, you label them sigma 1, sigma 2, sigma 3. You have to look at, arrange them in an algebraic manner, then only label as sigma 1, sigma 2, sigma 3. Is the idea clear? So, when I look at this expression, please verify with your computations. So, I have sigma cube minus sigma square sigma x plus sigma y plus sigma z, and I2 is obtained like this. I have sigma x sigma y plus sigma y sigma z plus sigma z sigma x minus tau squared xy minus tau squared yz minus tau squared zx, and then you have this I3s sigma x sigma y sigma z plus 2 tau xy tau yz tau zx minus sigma xs tau squared yz minus sigma y tau squared xz minus sigma zz tau squared xy equal to 0. See, you could have also written it from the determinant and arranged and grouped them. My interest is that you will also have to know what is I1, I2, I3, which are, because they are very useful if you know how to use them. When you do the computation, this is what I said. When you make the computation as engineers, speed is not important, accuracy is important. Okay, so you should have inbuilt checks in verifying your results. So, the roots of the equation are designated as sigma 1, sigma 2, sigma 3. Again, the labeling convention. See, the idea of repetition is that you should recognize that this is important. While learning a subject, healthy repetition is very, very important. Okay. See, now we will live in a two-dimensional domain. Okay, let me live in a planar situation. Even before I find out what are the expressions for principal stresses in 2 dimensions, you have them from your Mohr circle. So, whatever I do from a mathematical approach, it should satisfy identically. Only then my graphical approach is correct and my mathematical approach is also correct. So, you have to give credit to the pioneers that they have verified the development from multiple different ways. Okay. So, when I say 2 dimension, I have only sigma x, sigma y and tau xy are existing, all other stress components with z are 0. Okay. So, when I do that, I will have sigma z is 0 and this term goes to 0, this term goes to 0, these two terms also go to 0. And if you look at this expression, every term has a quantity which has a subscript z. So, all these quantities also go to 0. So, now this expression can be simplified and rewritten as sigma cube minus sigma squared multiplied by sigma x plus sigma y plus sigma into sigma x sigma y minus tau squared xy equal to 0. And I can take out sigma and I get a quadratic expression. Once you have a quadratic expression, you know how to find out the roots of the quadratic expression. But when you write the roots, it is directly not similar to what you got in Mohr circle. You have to do one more step of simplification, because you have this minus b plus or minus root of b squared minus 4ac divided by 2a is what you have generally learnt as roots of a quadratic equation. So, when you do that directly, I will get sigma 1 comma sigma 2 as sigma x plus sigma y plus or minus square root of sigma x plus sigma y whole square minus 4 into sigma x sigma y minus tau squared xy whole divided by 2. When I simplify this, this reduces to the same expression like what you have got based on the Mohr circle that we have seen earlier. There is absolutely no difference. So, these are very famous expressions. I have this as sigma x plus sigma y divided by 2 plus or minus square root of sigma x minus sigma y by 2 whole square plus tau squared xy. And from Mohr circle point of view, what is this expression? This was related to the radius of the Mohr circle. Okay. See, there by looking at the graphical representation, we were able to find out the principal stresses as well as its direction. Now, we will also have to find out the direction based on the mathematical approach. Okay. And before we go into that, let me also say, since you are very comfortable with Mohr circle, the stress state can be represented in terms of the principal stresses. It can also be represented in terms of any points forming the diameter of this Mohr circle. Is the idea clear? I can have multiple representation of the stress tensor. And why I call this I1, I2 and I3 are invariants? Suppose I start with my stress tensor referred to x prime, y prime, that must also give me the same principal stresses sigma 1 and sigma 2. Is the idea clear? It cannot give any other value of this, because it all represents what happens in a particular point of interest on all the possible infinite planes. The stress tensor per se can be represented with respect to xy reference, x prime y prime reference, 1 2 reference, or any other diameter. This is a very subtle concept. You know, this can be easily illustrated if you know Mohr circle, because we have spent sufficient time on understanding the Mohr circle. Now you are equipped. So, you can understand the roots of the equation, no matter what is the starting point of the stress tensor, should remain same. So, the coefficient should remain identical. The individual numbers for you to multiply and get the final value should remain same, but individual value can be different. That is what you see as different stress tensors. And this is also an inbuilt check when I want to find out stress transformation. Okay, I can use that as an invariant. Now, I said I have to find out the orientation of the principal stress plane mathematically. That means I should apply the condition mathematically. What is the definition of a principal stress plane? What is the definition of a principal stress plane? On the principal stress plane, you cannot have shear stress. So, I go and say in this expression, shear stress is 0, because this is a generic expression. You are finding out the stress transformation on a generic x prime y prime. This x prime y prime can coincide with your principal stress planes. So, this gives me again the same expression that we have got from Mohr circle, theta equal to 1/2 of tan inverse 2 tau xy divided by sigma x minus sigma y. So, you have a graphical representation, you have a mathematical development, both are identical. Is the idea clear? See, that is how scientific development has been. Now, we will also appreciate and put it in black and white whatever I have said. I can represent the stress tensor as sigma x, sigma y, tau xy, tau yx, or I can also express it in a simplistic manner as sigma 1, sigma 2, 0, 0. Is the idea clear? My reference axis become different. This you should understand. See, I have a populated matrix here. Here I have only the diagonal terms are available, non-diagonal terms are 0. It brings in lot of comfort in mathematical development. We will take advantage of this. Okay, we will take advantage of this. As I said, we have to utilize the invariants. This is again repetition of the same slide, where we have looked at what are I1, I2 and I3. So, look at this and understand how you get I1, I2 and I3. I have the 4 corner elements forming the third determinant for finding out this I2, and I3 is sigma x, tau xy, the complete matrix, and we will confine ourselves to a 2-dimensional representation. So, I have I1, I2 reduces to sigma x plus sigma y, and I2 is sigma x, tau xy and sigma yy. Okay. So, as I mentioned earlier, when you do stress transformation or when you do determination of principal stresses, you have an opportunity to verify your values. What way you will verify? Simplest one, at least you check whether I1 remains same when I go from sigma x plus sigma y to sigma 1 plus sigma 2 or sigma x prime plus sigma y prime. Is the idea clear? And I would expect you to do this verification in all your calculations. Speed is also important. When I say speed is not the only thing, that is the idea of saying that speed is not important, accuracy is more important. It is not that you say you said speed is not important, you give me 2 hours to solve a half an hour quiz. Do not do that. Okay? There is also a reasonable time in which you have to do it. This is not the only utility of invariants. From the Mohr circle, you can again reconfirm that you have the advantage that the stress tensor at a point of interest can be represented in multiple ways, infinite ways in fact. Okay? And some of them will be very simple, like when you refer it with respect to principal stress planes, you have zeros. Mathematics is simple. And you can also use the utility of invariants in many other ways. Okay, I have a uniaxial state of stress. Can you plot the Mohr circle for this? I have it. You can also draw it. And what we have learnt? We have learnt the uniaxial stress state can also be represented in multiple different ways. When I represent it in x prime, y prime or any of the other directions, the complete matrix will be populated. Fine. Now tell me, by utilizing the invariant, suppose I give a matrix which is populated, how will you verify whether it is representing a uniaxial state of stress? You have a clue right on your screen. You have a clue right on your screen. I say that you have to utilize the invariants. Please think about it. Okay. Think about it. And we will also see another important state of stress. What is this state of stress? It is a pure shear state. And you can also draw the Mohr circle. The graphical representation is very simple. The only thing is the origin is shifted. I shift the origin and I replot. And again, when I have a pure shear stress state, when I represent the matrix, in one reference frame I have beautiful zeros and the non-zero number. Pure shear stress state also has zeros and non-zero number. But when I go to the Mohr circle, I have infinite possibilities in which I can represent the same stress state. Is the idea clear? Now, with the utility of invariants, can you tell me how will I use the invariants to identify if a given matrix is corresponding to uniaxial stress state or shear stress state? Anybody? Very good, very good, very good. Because you know how to compute the invariants for this, and it is also a direct check that invariants are really invariants. So, when I have I2 is 0, I will have this as a uniaxial stress state. When I1 equal to 0, I will have that as a shear stress state. So, you should know, appreciate what are invariants, also assimilate what are invariants and use them in your computation. See, that is the purpose why you are learning it. Fine. And there are also advantages when I represent it in principal planes. See, we have earlier seen this Cauchy's formula, and we have also said that I should know how to write normal stress and how to write the shear stress in long expression, which we have already seen. I have shear stress is square root of Tn squared minus sigma squared n. I can find out this, and this looks very long and difficult to compute. Suppose I express the same stress state in terms of the principal stresses, all these expressions simplify. And not only that, researchers also wanted to develop new entities. Even for development of new entities, it was convenient for them to visualize when it is expressed in principal stress planes. Suppose I rewrite the same expression just to show that I am handling a principal stress plane. I have shown this tetrahedron in a different color, and mathematically, when you want to have a reference axis xyz, it is arbitrary. I can still put xyz in a convenient fashion and then say that they correspond to principal direction 1, 2, 3. Is the idea clear? In order to distinguish from a generic representation, I have changed the color of the tetrahedron, and I have also put this as only normal stress existing. And if you want to rewrite, you can also write it as sigma 1, 1, sigma 2, 2 and sigma 3, 3. Can you write the expression for normal stress and shear stress? Go from Cauchy's formula. find out what is Tn, find out Tn dot n, write the expression for normal stress, write the expression for shear stress. Please do that. Please do that. And then verify it from my expressions. I have very simple expressions for Tnx, Tny and Tnz. They are simply sigma 1 nx, sigma 2 ny, sigma 3 nz. And I have sigma as sigma 1 nx squared plus sigma 2 ny squared plus sigma 3 nz squared. Very elegant and nice looking compared to what we had seen for a generic representation of stress tensor. This is very elegant. And I also have the shear stress as Tn squared minus sigma squared. So I have Tn squared is sigma 1 square nx squared plus sigma 2 squared ny squared plus sigma 3 squared nz squared. And I can substitute it in this. I am showing the expression for you, okay, but I expect you to do that as a homework. Please do that as a homework. I want to give one more homework today. Fine. The next homework is, what is the relation between stress vectors on any two arbitrary planes? See, this is a very useful result. I take a point P, draw this sketch. I have a plane. The plane is represented by an outward normal and it has a stress vector Tn. I can also pass another plane n prime. I have an n prime plane. I have stress vector as Tn prime. And I want you to prove Tn dot n prime equal to Tn prime dot n. See, these are all vectorial quantities and this is a dot product. Please work it out in longhand and come with this identity, because we will use this identity to develop certain other interesting concepts related to state of stress at a point. So, in this class, we have looked at two more graphical representations of state of stress at a point. They showed that Mohr circle is by far the best graphical representation for state of stress. Then we mathematically developed what are the principal stress magnitudes as well as the directions, and in the process we identified a new set of quantities called invariants I1, I2 and I3. And I said that when you do the stress transformation or principal stress determination, you have an inbuilt check. If you check the invariants, your computation is correct. And I expect you to do that for whenever you are solving a given problem. And we have also looked at how to identify a given stress state is uniaxial or a pure shear stress state. See, in the early developments, people were struggling when they were understanding material behavior. They found uniaxial was easy to handle, biaxial some more understanding is required. So, even if you know the given stress state at a given point is uniaxial, the problem was lot more simpler. And looking at the stress tensor represented in terms of the principal magnitudes really helped the mathematicians to come out with newer entities. Okay, thank you.